Rates of change. So we want to figure out how a function changes over some time or at a particular moment. We know that for a line, the rate of change is simply whatever the slope of the line is. But for a curve, the slope is going to vary as we go. There are two types of rates of change we can think about. The average rate of change is when you select 2 points on a curve, connect them with a line, and you find the slope of that line. Remember that the slope of a line is given by y2 minus y1 over x2 minus x1, or rise over run. We can also write this in function notation as f at x2 minus f at x1 over x2 minus x1. This line I've drawn here is called the secant line. Finding the slope of that line, we say that it is the average rate of change of the function from this point x1 to this point x2. Contrast that with the instantaneous rate of change. That's trying to figure out how my graph is changing at a particular moment in time. This line I've drawn here is called a tangent line. It just skims my graph and it shares 1 point with my curve. It describes how my graph is changing at that particular moment. You can see that my graph increases, hits some maximum point, turns back around, etc. At each individual moment, the rate of change, or the slope of this tangent line, is going to vary. So let's think of an example that is pretty intuitive. You're going on a road trip. Let's say you're going to drive 200 kilometers. Things are going smoothly, but somewhere in the middle you hit traffic. You're pretty much stopped for a while. And then over here, you speed to make up for time. Your average rate of change is given by the total distance you traveled, 200 kilometers, divided by the total time it took, 2 hours, so 100 kilometers per hour. But of course, if you found your slope at each point along the curve, it would vary. Somewhere in the middle here, it would be very close to 0 or 0. If an officer pulled you over here when you were speeding and you said, "But officer, my average rate of change is 100 kilometers per hour," I don't think they'd let you off the hook. So big difference, average rate of change versus instantaneous rate of change. So for example, this parabola, y equals x squared plus 1. That's just your base or parent parabola shifted up 1 with a vertex at 1 here. To find an average rate of change, let's say between -1 and 1, we want to evaluate our function at each of those values, find f at 1 and f at -1. If I plug 1 into the function, that's equal to 2. And if I plug -1 into the function, that's also equal to 2. So the average rate of change from the points -1 to 1 is actually 0. If we simplify this, 2 minus 2, 0, over 2 is 0. If I drew my tangent line connecting those points, you can see that it would in fact be horizontal because the graph is symmetric. Connecting this point to this one, my secant line has a slope of 0. Now what I'm doing in the next examples is I'm actually bringing these 2 points closer together. So we went from -1 to 1. Now we're going to try from 0 to 1. So from the vertex to 1. Again, evaluate your function at 1 equals to 2. Evaluate your function at 0 equals to 1. And then you have y2 minus y1 over x2 minus x1. The slope from 0 to 1, if I drew my tangent line, is equal to 1. Let's bring the points even closer together. If I take the slope from the point 0.5 and 1, so some point in the middle here up to 1 there, plugging this into my slope formula, you'll find that the slope is 1.5. Now you can see what I'm doing. As this point gets closer and closer to 1, what we're actually doing is estimating the slope of the tangent line. If I put my 2 points close enough, my secant line essentially becomes a tangent line. Over here I put the points so close that the human eye probably couldn't even tell the difference. If you put the 2 points right next to each other, 0.99 or 0.999 and 1, it would basically look like a tangent line. So unfortunately, because we do not know calculus yet, that's the way we find the instantaneous rate of change, we have to estimate. We have to take a point very, very close to the point we want to find the slope at and estimate the rate of change from the point we want with a point very, very close to it. So here I have found the slope at 1. It looks like the closer the points get, the closer my slope is getting to 2. So it's safe to say that the slope of the tangent line at 1 is actually 2. And I've plotted it there. That seems about right.